All right, Calculus 30, this is review and preview video 2. I'm going to go into a little bit more detail here, some basics on factoring and simplifying rational expressions, maybe some synthetic division, factoring larger polynomials. So that's what I'm going to cover here in this little section. So factoring is probably the most important prerequisite skill for calculus that exists, and you're going to need to know how to. Factoring means basically splitting apart something into products, okay? So 2x plus 4, if we were to factor that, what I would have to do is try and write that as a multiplication of something. And of course, the first thing that you look for in any kind of series of terms here, or addition of terms in any polynomial, is you want to look for the greatest common factor. If you can pull or factor out a greatest common factor, that's going to be your first step always. So I see 2x and a 4 here. Okay, those are my two terms. And of course, there is a common factor of 2 that I would remove from this expression. What's left over when I remove or divide each term by my greatest common factor? Well, I'm left with simply an x here. If I divide 4 by 2, what do I get? Well, I'm simply left with a 2. And of course, this was a positive divided by a positive, so I have 2 times x plus 2. That's something very basic that you learned way back years and years ago. So we should know how to do that pretty easily. The second one here. Well, here we have a greatest common factor that is a combination of a number and a letter. So for example, I can take a 3 out of both of these terms, because there's a 3 as a common factor for 3 and 9. But I can also take an n. There is at least one n in each of these terms. So my greatest common factor is 3n. And when I divide that out, what's left over when I divide the common factor out here? Well, I'm left with n squared. When I divide 3n out here, I get simply 3. And this is a minus 3. Okay? Everyone see that now? Now, is this fully factored? Here's the question. Is this fully factored? Well, I can't really break this up too much more except 3 times n. Okay, so 3n is a single term. What about this though? In the past, we've studied something called difference of squares, right? So let's talk about that right now. Difference of squares. And what we have talked about is really difference of perfect squares. Okay? That's what we've studied, differences of perfect squares. And if we have something like n squared minus 4, I can factor that because this is a difference, a minus, of perfect squares. And there was a way we did that. So a difference of squares can be factored into 2 binomials where the first term in each binomial is the square root of the first term. It's a perfect square, so I'll put the square root here and here. The second term was always the square root of this, and that's nice and neat. It's a 2. And to get the minus, we simply put a plus and a minus there, and that's how we factor a difference of perfect squares. Well, in calculus, we are going to have to factor n squared minus 3 the same way. It's not a difference of perfect squares, is it? Because 3 is not a perfect square. But can we factor it like it's a difference of squares? Absolutely. The thing is that 3, if you take the square root of 3, it's simply square root 3. Okay? So watch this. Can I factor this more? Sure can. I'm going to go 3n times, I'm going to use my same method for factoring difference of squares. The square root of n squared is n, so n goes there and there. The square root of 3 is written as root 3. Yes, it's an irrational number, and we're not going to be rounding decimals in calculus. Okay? We're not going to do that. That is far too approximate. In calculus, one of the strengths of calculus is that we can be very, very exact. Okay? So we're not going to be using decimals. We're going to use something like this, the irrational expression root 3. And I'm going to do plus and minus. Boom. Well, there you go. Okay? So that's factored fully, really. Okay? So you can stop there. You can't take a common factor out of any one of these terms now. Okay? But that's just a heads up. You're going to have to factor a difference of non-perfect squares as well. Okay, moving on. X squared plus 7x plus 12. This is a quadratic. It's a trinomial, 3 terms. And the one nice thing about this is that the x squared term, or the leading term, has a coefficient of 1. This is the easiest of the quadratic types. That's why it's type 1 maybe. But what you do here is you try and find a number that multiplies to the constant term, plus 12, and also adds to the b term. If this is a squared plus bx plus c, ax squared plus bx plus c, then you want to find two numbers that multiply to 12 and add to 7. And those are the two numbers that are going to fill the last terms of the two binomials. So two binomials multiply to a trinomial, okay? So I'm going to put the x squared, I'm going to take the square root of that, I'm going to put x there and x there, similar to the difference of squares method. But now I am going to insert in these last sections here the integers that satisfy these conditions. They multiply to positive 12 and they add to positive 7. And what are those two numbers? 3 and 4. And this is where you put the signs in there too. This is obviously a plus 3 and plus 4. Okay? So that's how you factor this trinomial. And you don't believe me? Well, if we were to multiply this out, we should get the original question back. How do we multiply this out? FOIL method. Who remembers FOIL method? Yay! FOIL method. So what do I do FOIL method? First term times the first term. That's the f in FOIL method. That's x squared. O is outside terms. X times positive 4 plus 4x. I is inside terms. That's plus 3x. And L, to complete the FOIL method, is the last terms you multiply. And so that's going to be plus 12. Combining like terms, you get x squared plus 7x plus 12. Now, I know this is probably baby math for you guys, but, you know, here we go. I'm doing it anyways. Okay. X squared plus 13x plus 30. Again, it's a 1 there, so I simply go ahead and put the square root of this. That's x times x. And two numbers that multiply to 30 and that combine together to give me plus 13 is going to be, if you said 15 and 2, you would be wrong. Because 15 times 2 is 30, but 15 plus 2 is 17. So that's not going to work. 15 and 2 isn't going to work. 15 minus 2 is not going to work either because this is a positive 30. And 15 times negative 2 gives us negative 30. So the only options here are plus 10 and plus 3. Okay? If I had this, oops, minus 30, that's when you would say, hey, this is a negative 30, so I am going to go with plus 15 and minus 2. Then you're good to go. Okay? All right, factoring quadratics, number 2, is when we have a leading coefficient. So on the leading term, the coefficient is called the leading coefficient. If this is something other than 1, we might want to factor the quadratic a different way. You can certainly do this by sight or by intuition, which at this level you probably are pretty good at, which means this. If you just take a look at this, you know a couple things. You know that the first two terms here, this one times this one, have to equal 6x squared. There's a limited number of possibilities. It could be 6x and x. It could be 2x and 3x, right? Usually if you're going to guess, you want to maybe start with the ones that are closest together, like 2x and 3x. That's just a hint. Most of the time, these are going to be your first terms, the ones that are closest together. So you do that, and then you're going to try this anyways. You don't know if this is true or not. But now you pick factors of negative 35. And how do you determine which factors are appropriate? Well, the quick FOIL method that you would do, the middle terms have to add up to positive 11. So what do I mean? Well, 35. Okay, what's that going to be? 5 times 7. Well, it could be plus 5 and minus 7, or minus 5 and plus 7, right? So let's just try those. Let's say plus 5 and minus 7. Just randomly, going to throw those in there. Now, is this correct? Well, a quick FOIL would determine that. So 2x times 3x is 6x squared. This is going to be minus 14x, right, plus 15x. Minus 14x plus 15x. Ooh. Minus 14 plus 15 gives us plus 1x. That's not what I have here. Okay? So it looks like I'm going to have to mix this around a little bit. So I'm going to change that. So let's say, what about if there was a what about minus 7 here and plus 5 here? Okay, and again, there's going to be some trial and error here, so I'll speed this up a little bit. So a quick FOIL method again, this is 10x minus 21x. Do you see that? See, 10x minus 21x. Oh, we're really close. 10x minus 21, that's negative 11x. So I know that my signs are mixed up. That's all I have to change now. So I have to make that a minus and this a plus. Then we have minus 10x plus 21x. Done. Okay. So again, I don't know where you're at with that, with factoring like this. I don't know where you're at with that. If that makes sense, if you can do that, no problem. Great. The other method is the decomposition method, which I probably won't go over in this video. You can look up Foundations of Math 10 decomposition method. That's where I do a whole lesson on that. And it includes multiplying the 6 times the negative 35, which I've done here, to get a certain number. And you pick 2 factors of this number that would add up to this, and then you factor by grouping. So that's the decomposition method. I'll leave that to another video, but that's another way you could do that if the intuition method is failing you. Okay? All right. We took a look at difference of squares already. So these are 2 examples of differences of squares. And you might say, this one does not look like a difference of squares. Well, remember, in calculus now, we're going to be factoring differences of non-perfect squares, and that's going to be okay. Okay? So watch this. This one over here, you could factor as a difference of squares. You could say, I got 2 binomials. The first term is going to be the square root of this first term, which is root 3x. See that? Root 3x. That's the square root of 3x squared. It's not a perfect square, but you can treat it as a square. What's the square root of 5? Well, no problem. Root 5. Root 5. See, it's the same method, right? And then plus, minus. Boom, done. Before I didn't really need you to factor this because it wasn't perfect squares, right? What's the difference of perfect squares? But now in calculus, we need to be prepared to work with some rationals, okay? And of course, this one here, right? 2x minus 5 and 2x plus 5, right? The other thing you want to be careful of is take a greatest common factor out to first, if possible. So for example, you have 2x squared minus 8, and you say, you know what, I can't, that's not perfect squares. I can't factor as a perfect squares. But what you could do is you could take a 2 out, right? Now you have perfect squares. This is easy. So it's 2x minus 2 times x plus 2. It doesn't matter if the minus 2 is before the plus 2. Doesn't matter, remember, because you're multiplying. So order doesn't matter there. Okay? All right. Now this is actually in your calculus textbook, okay? The Red Stewart calculus textbook here, and I've just clipped this out. I'm going to do a couple examples of factoring sums and differences of cubes now, okay? This is something that we haven't really studied much before, but again, you're going to need to know how to factor a sum and difference of cubes. All right, so as we continue on, you can factor a sum of cubes. You can't factor a sum of squares, but you can factor a sum of cubes. I'll show you. Here is the this is the template really for factoring sums and differences of cubes. This is a sum of cubes. That's a perfect cube, x cubed. That's a perfect cube, 27. Okay, so we can factor this pretty easily using the sum of cubes formula here, right here. So if you have anything in the form of a cubed plus b cubed, you can factor it like this: a plus b, which is the cubed root of the first term, plus the cubed root of the second term. That's the first binomial. And then the second factor is a trinomial that goes like this: a squared minus a times b plus b squared. And that's kind of a shortcut to factoring a sum of cubes. So watch this. This would go like this: x cubed plus 27 would be equal to this. The cube root of x cubed is x. This is going to be a plus. If that's a plus, this is a plus. Notice that the sign is the same there. So it's going to be plus the cube root of 27, which is 3. The second factor is going to be a trinomial given by a squared. So that's x squared minus a times b, or 3x, plus b squared. Plus b squared is 3 squared is 9. So this is the factored version of this sum of cubes. Okay, so this is just a new it's a new sort of template for you to use in factoring. Okay, sum of cubes. Now the difference of cubes. The difference of cubes. Let's see. What are we going to do here? B. Let's take a look at B. Okay, get rid of some of this. B. 2x to the fourth minus 18x squared. Now it's interesting here. Remember, we need to take out the greatest common factor. I see that there's a common factor here. So let's take out what? A 2x squared. That's the common factor I can take out of here, the greatest common factor. So I'm left with what? X squared minus 18 divided by 2 is 9x squared divided by x squared. Okay. Okay. Okay, this is a difference of squares question, isn't it? Now you see it? So 2x squared, we did this already, x minus 3, x plus 3. Did something like that already, okay? So that, even though it looks like it's maybe a difference of something strange, it's still just a difference of squares, okay? Let's do this difference of cubes down here to get a difference of cubes example. This is a perfect cube. This is a perfect cube. That's 2 cubed. So factored form would be cube root, that's x. This, if it's a minus, notice the minus this is always the same sign right there, the first factor. So it's going to be x minus 2. And then you simply do x squared. This sign is always opposite of whatever you're given. You see, plus there if that's a minus, and minus there if that's a plus. So the signs are same, opposite, and always positive. Same, opposite, always positive, if you're memorizing this. If you memorize this, it's going to maybe speed things up a little bit for you. If you have to refer back to it all the time, it'll slow you down, but try and memorize it if you can. So same, opposite, so this is going to be a plus 2 times x, and this is always positive at the end here. 2 squared is 4. Okay, and notice this trinomial can't be factored. There's no two integers that multiply to 4 and add to 2. 4 and 1 and 2 and 2, they don't add to 2, so this can't be factored. You're done. Fully factored. Any questions? All right, so a couple more examples before we complete this review and preview section here. One of the things that we're going to be really required to do in the next couple sections is to simplify rational expressions. Sorry, that's really messy. I tried to be as messy as possible so you couldn't read it. Simplifying rational expressions. So a rational expression is where we have a ratio of polynomials, basically, a ratio. Now, how do we simplify that? Well, the steps that we have learned in the past, and you've learned this before in previous classes. First of all, what we do is we remove greatest common factors from both the top polynomial and from the polynomial in the denominator. If we can do that, we should do that. And in this case, we can. We look at these 3 terms, and I can factor a 2 out, for sure. A 2. Oh, sorry. How's that? Is that better? Sorry, I just had myself muted for a bit. I could see what that chat was about. Okay, hopefully you can hear me there better now. Sorry. Hi. Okay, so if we can take a greatest common factor out, we should do that. And I'm going to take a 2 out of this top. So that's going to leave me with 2x squared minus 7x minus 15. Okay? And on the bottom, I can also take a greatest common factor out or remove a greatest common factor, a 2 as well. So this is going to be x minus 5. Okay? So once we remove greatest common factor, we can see that simplifying, this is going to be pretty easy. Like a 2 over 2, that just divides out to a 1. So really, that 2 can be removed from top and bottom, divided. Now, have I simplified much? Not really. There's more simplification I can do. And the step 2 says fully factor numerator and denominator. Okay, so let's factor the top and the bottom. Well, the bottom looks pretty factored. It's prime. You can't factor it anymore. But the top, it appears that we may be able to split this into 2 binomials. So let's try and do that. So factoring by intuition here, I'm going to say Well, if I've got a 2x squared there, it's probably going to be a 2x and an x. Those are the only two factors for 2x squared, really, where you split up the x's anyways. And so I've got 2x and x, and 15 is going to be probably 5 and 3, probably not 15 and 1, probably 5 and 3. So check this out. If I have a 5 here and a 3 there, I look and I say, hey, that could be a 10x, this could be a 3x. Guess what? 10 and 3 can combine to 7 if I have positive 10 and negative 3. So again, that's how you factor this quadratic. That's 2x times x is 2x squared. We have 10x minus 3x is 7x. And then negative 3 times 5 is negative 15. So I've factored the top and the bottom. I've done step number 2. Now here's an important thing, because in these questions that we're going to be studying in calculus, we're going to have to note restrictions. So when we come up with a mathematical explanation or description for something, in real life terms, we may have restrictions. So it could apply to everything except for this one piece of time, or this one length, or this one volume, or this one whatever. So this one aspect could be a restriction. And what we have here is we have a restriction on our variable x. I don't know if you can see it, but this is a dividing, right? Divided by. I cannot divide by what? What can I not divide by? I can't divide by 0. So the x value that causes this to be 0 is restricted. I cannot, this works for everything. This is a simplification for every x except for x equals 5. So my restriction is x cannot equal 5. And the reason why I want to do this now in step 3 is because step 4, we divide out all the common factors. And this, as we see, this is actually, oh, my bad. Okay, nobody noticed that? So this actually, look at this, guys. 10 minus 3 is positive 7. So this is, oh, I caught my own mistake. Okay, if you caught that before me, congratulations. But anyways, this should be an x minus 5, and this should be 2x plus 3. So now, as I was saying, we do have a common factor that is divided out here. Those two are gone. And what I'm left with is the simplification is 2x plus 3. But the important part of the simplification is that x cannot equal negative 5 because it makes this denominator equal to 0. Okay? So that's simplifying rational expressions. We're going to need to know how to do that in section 1.1 and 2. The final example I want to go over with you here in this preview, I'll just do this one. I'll cut this video a little bit short here. I won't do the second part. But in order to rationalize, if we have to rationalize an expression, that means we get rid of the radical. Instead of having it irrational, we make it rational. So that means we need to eliminate the radical. Now we're only going to be able to eliminate the radical in either the numerator or the denominator, probably not both in most cases. So this example asks us to rationalize or make rational the numerator in this expression. So how we do that is this. And this is going to be something that might be kind of foreign to you. You might not have learned this before. But if you want to, if I want to get rid of, let's say, a root 3, I could square it. That would get rid of the root 3. Or multiply it by another root 3. See that? That becomes 3. The rational is gone. So if I can multiply the top and the bottom by the same thing, I'm not actually changing the expression. And what you want to do is you want to multiply by the radical conjugate. So in this case, if I wanted to get rid of the root sign in the numerator here, I would multiply both the top and the bottom by the conjugate of this. And the conjugate means it has the same terms but opposite sign. So this is the radical conjugate. So I'm really just multiplying the whole thing by 1 here, right? That's 1. That's 1. So I can do that. And what does that do for me? Well, what you notice here, or you should notice, maybe I'll zoom in a bit small. What you should notice is that we are going to have a difference of squares when I multiply two of the exact same binomials, the only difference being the sign in the middle, plus minus. that's going to come out to a difference of squares. So what's root x plus 4 times root x plus 4? Well, that's like root x plus 4 squared, which just gives me x plus 4. Okay? Root x plus 4 times root x plus 4 is root x plus 4 squared, which those cancel out. It's just x plus 4. Now I'm going to have plus 2 root x plus 4. And then if I FOIL here again, minus 2 root x plus 4. And then minus 4. That's what you have when you multiply all that out. I'll get rid of some of my markings there so you can see that. Okay. And then on the bottom, we're going to leave this in factored form, really. This will be handy later in calculus, but I'm not going to multiply that out just now. Okay. So what I can do here now is gather like terms. Those two terms are gone. These two terms are gone, plus 4, minus 4. You're just simply adding them up. They're gone. And so what I end up with is, I end up with x on top, x on the bottom, times root x plus 4 plus 2. And the reason why we leave this factored is because we may be able to further simplify. And in this case, we can. So there would be a restriction here. Not going to worry about restrictions for this one today. But x and x be gone, right? And so we would end up having 1 over root x plus 4 plus 2. And again, restrictions, I won't get into restrictions for this one. But the simplification or the rationalization, notice that the numerator is rationalized. The denominator is not, but that wasn't the question. It was just to rationalize the top, and that's how you do that, okay? So that's going to come into play a little bit later in this calculus course, okay? So there's your review and preview section, part 2, focused mainly on factoring, and now you're ready to dive into calculus.